Okay, this episode of our screencast deals with the square nature of electrical forces. Just like gravitational forces, it turns out that the electrical force is based on the inverse of the center to center distance squared between the two objects. Now, this gives a lot of students trouble. They have no problem with the inverse part, but they seem to have a difficulty with the squared part. So as a reminder, if we double the distance, we go from 20 to 40 centimeters, then we've gone from essentially 12 to 3, that's 1/4 as much force. So it's not half as much force when we double the distance, it's 1/4 because it's 2 squared or 1 over 2 squared, so 1 over 4 or 1/4 less. If you go from 20 to 80, that's going to be 4 times more distance, but that's going to be 1/16 as much force. Okay, so it's inverse square, not just inverse. Now, whenever you're checking the effects of charge, distance, on the amount of force between two objects, keep in mind that the electrical force is going to be based on K, which is a constant. So in this case, constant means it's not going to change. So we're okay there. Times the charge, the first charge. Now it's Q1, Q for charge. It can be capital Q or small q. It doesn't really matter. Q2 over the distance between them squared. Now, if you change any of these values, keep in mind if you put a number out in front of any of these, if it's the distance, you have to square that number. If it's these two, you're going to have to multiply the effects of those numbers. Okay, so in this one, we're starting off at 0.080 newtons. Now, if we double one object's charge, that'll put a 2 in front of that. Then that means the overall impact is essentially going to be to double that force, so it's going to be 0.16 newtons. Now, if they have a force of 0.08 newtons again, and we double the charge of both of the objects, then that's like putting 2 times 2 in front of each charge. So that's going to make the overall force go up by 4. So now we're talking about 0.32 newtons. All right, now the distance, again, it's 1 over the distance squared. It's the inverse of the center to center distance squared. So we start at 0.08, and we're going to double the distance. Now that means 1 over 2 times the distance squared. Now again, 2 squared is 1/4. So I have to divide the 0.08 by 4, and I get 0.02, or 4 times less force. Skip that problem a little bit. Go back to number 4 there. Two charged objects have a repulsive force of 0.08 newtons. The distance between them is tripled. So again, it's 1 over 3 times the distance squared. Well, 3 squared is 3 times 3, so that's going to be 1/9 as much force. So I have to take 0.08 and divide it by 9 to get the actual value. So that's essentially going to be equal to 0.009 newtons, 9 times less. Okay, so we got the 0.080 newtons. Now we're quadrupling the distance between them. So 1 over 4 distance squared. Now 4 squared is 16, so we're talking about 16 times less. So we're talking about a pretty small force there compared to the earlier forces. 1/16 of the very initial force, 0.005 newtons. Okay, 6. Now we have the distance. Now this can get tricky. We're getting closer, so I should expect my number to go higher. Okay, whenever you get closer, the value of the force should go larger. The reason that works out is it's 1 over 1/2 times the distance squared. Now 1/2 squared is 1/4, mathematically speaking. This is where a good knowledge of fraction and ratios comes in. That's 1 over 1/4, and dividing by 1/4 is exactly the same as multiplying by 4. So it's going to be 4 times more than it was. So we'll be back up to a large number, 0.32. Same impact is doubling both of the charges. Okay, now if we start changing both of them again, some will make it go up, some will make it go down, and all we have to do is look at the overall effect. So 0.080 is our first number. If we double 1, then that's going to be 2 times larger. And then the distance is also doubled. Now again, that effect is 2d squared. So I'm going to end up with an overall effect of 2 over 4, which is 1/2 as much. So 0.04 newtons. Okay, now this time we're doubling both, and we're doubling the distance. So we're going to have 2 times 2, which is an increase of 4, and then we have to divide by 2 times the distance squared. Well, 2 times 2 is 4. 2 squared is 4. So essentially in the end we're going to multiply by 1. So we're back to 0.008 newtons, no change. Okay, 2 charged objects have the same force, the 0.08 newtons. If we increase the charge of 1 by 4 and the distance by doubled, what's the overall impact on the new force? What is the new force? So we're 4 times the first force. Now, not to multiply by anything else because it's only, one charge that we're changing. And then where you are at the same time, distance is being doubled. So 2d squared. So that's going to make 4 over 2 squared is 4. So again, just like the one above. Now keep in mind, if I double both, they become 4. If I quadruple 1, then the increase is 4. So it doesn't matter which ones I increase. It's the overall net effect on their product. So we're still at 0.08 newtons. And then finally, this last one, charge of 1 is tripled and the distance is tripled. So we're going to have a 3-time impact from the tripling of 1 charge on top. And then we're going to divide by 3 times the distance squared. Well, that's 3 over 9. 3 squared is 9. That's 1/3 of what it was before. So if we take 0.08 divided by 0.08 divided by 3, we get 0.027 newtons, 1/3 as much as it was before. So it's the exact same relationships we worked at with gravity. Gravity, universal gravitation, and Coulomb's law of electrical forces are going to have exactly the same relationships. The biggest difference is that gravity is a much weaker force. It takes a lot of mass to get a little bit of gravitational force. Whereas electricity is a pretty strong force, so it's hard to build up a lot of charge in one place, so you get large forces for a relatively small amount of charge. And that's it for the inverse square nature of Coulomb's law. We'll be moving on to electric fields next.